Okay, let's get started. This is lecture 6 about the extension of the results of chapter 4 to cases, to models in which we have stochastic shocks to the return function. And our ultimate goal is to use the results of chapter 4 in these cases, and to do so we need some probability theory and the theory of Markov processes to see that the extension can be almost immediate. So we will need to do some groundwork, but in the end we will see that the extension it's not too demanding and it's almost immediate. How to extend the results of deterministic dynamic programming is the topic of chapters 7 and 8 in the textbook. So this lecture and the next one is about this lecture and the next one is about the main results. We will have some formal proofs, but instead of providing the formal proofs which you can find in the literature, not only in our textbook but in many other books and sources, I will try to put all the materials into a coherent picture, into a coherent story, which you may find useful in treating stochastic dynamic programming. So first of all, to start the groundwork, let's talk a bit about the different kinds of stochastic shocks. They can be discrete or continuous. Discrete shocks are the more comfortable version of stochastic shocks. They can be finite or countably infinite. Plainly put, a discrete stochastic shock is the case when the shock variable take on distinct values from a set, and all the elements in this set have distinct probabilities, of course non-negative probabilities, and the sum of these probabilities is 1. So, for instance, the simplest case, we have two distinct outcomes in a model in which, for instance, the economy may be in recession. This is the one possible outcome, recession. The other possible outcome is boosting the economy, and the first outcome have the probability of 0.3, and the other possible outcome have the possibility or probability of 0.7. So 1 altogether, the sum of probabilities is 1. So this is a very primitive example, but this is what we have. The other case of stochastic shocks, the other version of stochastic shocks, is continuous stochastic shocks, in which the random variable moves in a closed interval, and we have a continuous density function with the property that the density function assigns non-negative values to any event, and as you may know from elementary probability theory, integrating the density function over the interval from which the random variable takes on its values, we have 1. So as we will see, in these cases we use probability measures, different forms of probability measures. You can see that if the random variable is discrete or it's continuous, we have different probability measures, And this is one of our goals, to build a theory, to build a framework in which we can treat these cases in a unified way, in order not to have to choose between different frameworks. We need a unified framework in which we can treat discrete and continuous stochastic shocks, random variables. In all these cases, even if we have a discrete random variable or a continuous random variable, we have the functional equation. You can see it in the slide. Here, as I promised in the first line, very first line, there is a stochastic shock to the return function. So there is a random, in this framework, we have a random productivity shock to the production function. X stands for current capital stock, Y stands for capital stock next period. This is the choice variable. And Z prime is shock next period, which is unknown when the agent makes his or her decision. And most importantly, you can see in the second half of the functional equation, we have an expected value of the functional equation for the next period. So this lecture and the next one is about how to build a framework in which we can deal with the expected value of a function. So, as I have just mentioned, we are about to use probability measures. They are functions on the state space that assign values, probabilities, to subsets of the state space. Plainly put, if we have an interval on which the continuous random variable moves, we want to know the probability of the event when the random variable falls into a certain subset of this interval. So the question for this lecture is how to have such probability measures. Such a probability measure, let's call it mu, which is a function, has some simple but key or crucial features. One of these key features is non-negativity, and the other is additivity. And let's focus on the latter now. Let's have a simple example of throwing a dice. Now the state space are events of throwing 1, 2, 3, 4, 5, and 6, and all of the events have the same probability of 1/6. In this case, this is a very elementary example. The probability of having odd is the sum of the measures or the probabilities of the disjunct sets of throwing 1, 3, or 5. Altogether, this is 0.5. The probability of having even is also 0.5. We need to add up the probabilities of throwing 2, 4, or 6. Please be aware of the fact that there is a special emphasis on disjunct sets. So we cannot throw 1 and 3 or 3 and 5 at the same time. So in general, for disjunct sets, which can be events in the case of a probability measure, this additivity or adding up property, which I am emphasizing, means that the measure of the union of the disjunct sets is the same as the sum of measures of disjunct sets. This is very crucial and very useful. So this is a property we insist on. So this is a property we won't have for any measure or probability measure. We have a problem here because for discrete variables like throwing a dice, a measure is defined for all subsets. So it's easy to count all the possible events, like the probability of throwing 1 or 2, 3 or 5, or the probability of throwing 4, 5, or 6. The letter is 0.5. In this case, when the random variable is discrete, the measure, this probability measure, naturally has the adding up property. However, in the case of uncountable random variables, like an interval and a closed interval, we have infinitely many subsets, and we cannot consider all the subsets when the random variable moves on an interval. And if we wanted to do so, we would end up in infinite sums, and in the end we won't have the adding up property. For instance, here you can see a very simple example. We have a state space for the random variable in the form of this closed interval, and we can see that the measure of the entire state space is finite. This is an interval, so we have infinitely many subsets. We can divide the state space into infinitely many subsets, and all of them have non-negative, very, very, very small, but not zero probabilities. So in the end, when we wanted to add up the probabilities of these disjunct sets, we couldn't have a finite measure for the whole state space. So this problem is a crucial problem because normally we want to have random variables moving on intervals, and at the same time we want probability measures which have the adding up property. So we need a way out, and this way out is to define measures on smaller or narrower families of subsets, and to make it sure that the measure defined on this narrower family of subsets of the state space can be applied to the broader family of subsets of the state space. This is the strategy. Before digging deep, let's have a look at the agenda for this lecture. We have, as far as I am correct, we have 4 points to touch today. First, we will identify the sets on which measures can be properly defined. We need measurable spaces, so we will define them. We will list their key characteristics, so we will learn a lot about measurable spaces. This is the first step to take, and the second step to take is to define measures. This is very natural. If we want to measure measurable spaces, we need measures. This is very natural. This is obvious. We will define measures and we will survey their key characteristics. Then, as the third step, we want to understand how to interpret, how to understand, and how to describe the expected value operator for functions. This is just a kind reminder. In the introduction for this lecture, we saw that the functional equation in a stochastic case, the functional equation contains the expected value of the value function, and this is what we want to understand, how to do this, how to solve such problems. In discrete case, we have no problem. In discrete case, such an expected value can be expressed as the weighted average of value functions. So, as the textbook explains, in discrete case, the results of chapter 4 can be immediately extended to stochastic case. However, in continuous case, we need measurable functions to move on. So we will learn about measurable functions. We will define them. We will try to understand their key features. And given that in continuous case, the expected value of the function is expressed with an integral, we will build a simple and straightforward theory of integration. This is the Lebesgue integral, to interpret the expected value of functions for continuous random variables. So this is what we are going to do in turn. But before digging deep, we have a warning. I'd like to warn you that chapter 7 of the book, which we are dealing with now, is very technical and very brief. So users are strongly encouraged to use Robert G. Bartle's The Elements of Integration. This is a very brief but very nice textbook on measures and integration, and this is the book, more importantly, this is the book what Lucas and Stokes used when writing the book. So chapter 7 is in close line with Bartle's book on measures and integration, so this is very, very useful, including the exercises. Okay, let's start with the measurable spaces. If we have a set which we call a state space, on which family, this is the question for us for now, on which family of its subsets should we define measures? So we are looking for the adequate, the best, the most suitable family of subsets to define measures. This is not an easy question because most of the sets have various, more than one families of subsets. So first, let's have a definition, the definition of the sigma-algebra, which is a key concept for us today. The sigma-algebra is a family of subsets of a set, and it has some key features. I listed these key features in 3 points. You can see that the empty set and the whole set is the element of the sigma-algebra. If a set is in this is the first key feature, the empty set and the whole space is in the sigma-algebra, in the family of subsets. If a set is in the sigma-algebra, its complement is also in the sigma-algebra. And if a series of subsets is in the sigma-algebra, its union, infinite union, is also in the sigma-algebra. If a family of subsets fulfills these characteristics, if a family of subsets has these characteristics, we call it a sigma-algebra. Okay, further definitions. If we have a set, and if we have a family of subset, a sigma-algebra, so if we have a set and a sigma-algebra of whatever type having these characteristics, we have a so-called measurable space. Any set, so a measurable space is a pair. The first half of the pair is the set, and the second half of the pair is the sigma-algebra. This is a measurable space. And any set from the sigma-algebra is a measurable set. Here I listed some examples from Bartol's book, 2.2 examples on pages 7 and 8. He has lots of examples, so this is just a selection. Let's focus on the most interesting cases. The first one is an interesting case because we have a set X, and we have a sigma-algebra that consists of all the subsets of X. Here we have a conflict, and this is the conflict I want to highlight now, because if the set is countable, then it's no problem to define the sigma-algebra consisting of all the subsets of X. But if the set is uncountable, continuous, then defining the sigma-algebra as the family of all the subsets of the set is still available as an option, but it's not too useful. So if we have, practically speaking, if we have an interval which defines a continuous variable, so if we have an interval as the set, we can define the sigma-algebra as the family of all the subsets of this interval, but it's not too useful because of the problems with the adding up property I have just mentioned. So once again, it is possible to define a sigma-algebra in the case of a continuous variable. It is possible to define a sigma-algebra as the family of all the subsets of this interval, but it's not too useful. The next interesting case is case 4. 1, 2, 3, 4. Yes. If we have two sigma-algebras, x1 and x2, so they are two sigma-algebras, which means they have the properties, the necessary properties, their intersection is also a sigma-algebra. This is an exercise both in Bartol's book and both in the Stokey-Lucas book. And let's stop for a minute. If x1 and x2 are sigma-algebras, they both have the empty set and the whole set. So the empty set and the whole set is in the intersection. So the empty set and the whole set is in x3. If a set is in both of them, then its complement is also in the intersection. And if a series of sets is in both of them, it's gonna be in their intersection. And given the fact that they are closed as sigma algebras, they are closed under um, infinite union. Their infinite union is also in the intersection, so the intersection is also a sigma algebra. It can be proven formally, but trust me, the formal proof is based on this line of path. Okay, and the last point is also important. This is the famous and very important Borel algebra. If we move on the real line, so if we work with intervals on the real line, we have the so-called Borel algebra, which consists of open intervals. We will see that the Borel algebra contains all the closed intervals. So if we move on the real line, the related sigma algebra is called the Borel algebra in one dimension case. It can be extended to any dimension. So we can have the Borel algebra for 2-dimension points, for 3-dimension points, and the like. Any set in the Borel algebra is a Borel set. So most of the time we work with Borel sets in our models. Please remember, this is just a kind reminder. In chapter 4 we saw that in order to have problems which can be solved, we need bounded returns, and if the return function is unbounded, we can make it bounded by forcing the variables into intervals, closed intervals. And in this case, when we follow this strategy, we work with a Borel set. So practically speaking, in such a case, the variable is forced into a Borel set. So the Borel sets have special importance to us. When the set on which the random variable moves is continuous, we cannot define an appropriate measure on the sigma algebra if the sigma algebra contains all the subsets of the set. Simply put, this is too big. So we need to follow a different strategy. We need to find a smaller family of subsets, which is a family that contains the family of subsets we are interested in, whatever they are. So if we want, practically speaking, we want to focus on a distinct family of subsets, and luckily there is always a sigma algebra which is the smallest one that contains the family of subsets we are interested in. This is just a reminder because we covered this problem in the previous slide. So if we have a family of subsets which is important to us for any reason, there are various sigma algebras that contain this family of subset. Let's call it A. So there are various sigma algebras that contain this family of subsets which has special importance to us, and there is always a sigma algebra which is the smallest one of all the sigma algebras that contain this family of subsets we are interested in. This is the intersection of the sigma algebras containing the family of subsets we are interested in. this is just a kind reminder. So the intersection of the sigma algebras that contain the family of subsets we are interested in is always a sigma algebra. So this is a way out. We can find, practically speaking, this is good because we can always find the smallest sigma algebra that contains the family of subsets we are interested in. Once again, about the Borel sets, we have already covered some introductory ideas on Borel sets. I mentioned a couple of minutes ago, I mentioned that most of the time we work with closed intervals, which is a Borel set. So it's an interesting question how to define a sigma algebra to such an interval. This is what we cover here. This is the Borel algebra. Borel algebra belonging to any closed interval consists of sets, practically speaking, intervals in any dimension. They can be one dimension closed intervals, they can be 2-dimension, 3-dimension intervals. A 3-dimension interval is a 3-dimension point, set of points, practically speaking, in which all of the 3 coordinates move on distinct closed intervals. Okay, so in the simplest case of a 1-dimension interval, the Borel algebra consists of sets consisting of closed intervals, and these closed intervals belong to the set we are interested in. So practically speaking, the Borel algebra consists of subsets of the interval we are working with. This is just a very quick exercise related to the previous slide. We want to show that the sigma algebra, I mean the Borel algebra, of all open intervals also contains all the closed intervals. This is a very simple exercise. We need to use the fact that a sigma algebra is closed under complementation and countable union. Hence, it is also closed under countable intersection. So all we need to do is to find a sequence of open intervals in this form, and the intersection under which the sigma algebra is closed, the intersection of these open intervals is the related closed interval. So the Borel algebra of all open intervals also contains all the closed intervals. This is an important exercise because most of the time in dynamic programming problems we work with intervals, closed intervals. So in this exercise we are supposed to show that the family of subsets of a closed interval is a sigma algebra. At the bottom line, we need to show that all the key features of sigma algebra hold in the case of the family of subsets of a closed interval. Instead of repeating what you can read in the slide, I just want to highlight the main idea behind solving this exercise. All the subsets of a closed interval, you can see the definition of the family of subsets of the closed interval we are working with. So we need to use the fact that the sets, the subsets in the family of subsets, or subsets of the state space, and they come from the Borel set. So, for instance, the empty set and the whole state space are in the family of subsets because they are subsets of the state space, and at the same time they are in the Borel algebra. We need to do this in the remaining two cases, in the case of the remaining two features. So in the end, the family of subsets of a closed interval, any closed interval, is a sigma algebra. That's all to that. Let's go on with measures. We need functions that assign values like size or probability. Please remember your studies in probability theory, in which probabilities were described by areas, for instance. So this is a good analogy, I guess. So these functions assign values to any subset of the state space. Such a function is a measure. So first of all, let's define measures. We have a measurable space, which means that we have a set and we have a sigma algebra of the subsets of this set. And the measure is an extended real function. Extended real valued function means that the function may take on infinity, positive infinity. This is extended real. This is what we mean by extended real valued functions. So we have an extended real valued function which, to be a measure, it must have three properties. For the empty set, the measure is 0. The measure for any set is non-negative. And if we have a sequence of disjoint subsets in the sigma algebra, then the measure of the union, of the infinite union of these subsets, is equal to the sum of measures of the disjoint subsets. This is the adding up property we insist on so much. So if we have a measure, the measurable space turns into a measure space, which is a triple consisting of the set, its sigma algebra, and the measure which is defined on the sigma algebra. Another important definition, mu almost everywhere. It may be challenging to fully understand the concept of mu almost everywhere, but trust me, this definition has special importance in integration theory, so we must address this definition. So we have a measure space, set, sigma algebra, and a measure, and we say that a proposition like a function e is equal to 0, or a series of functions converges pointwise to a function. So this is a proposition. This is a characteristic that holds mu almost everywhere if there is a set in the sigma algebra which has 0 measure, and the proposition holds on the complement of this set. So practically speaking, we have a proposition that holds on a given subset of the state space of the set we are working with. So there is a proposition that holds on a distinct subset of the state space, and the complement of this set has measure 0. I know it may be challenging, and it doesn't seem to be very practical at this point, but trust me, very soon I will show you one proof, a proof in which we will play on this concept of mu almost everywhere. Okay, there is a special measure. I mean special because it has special importance to us. This is a probability measure. We have a state space for a random variable, so let's switch to the language of probability, basic probability theory. We have a state space for the random variable, which is a closed interval. The measure of the whole state space is 1. This is probability 1, which means that the probability that the random variable falls into this interval, which is the whole state space, is 1, because the random variable cannot fall outside the state space. And the subsets of the state space are events. For instance, we have another interval which normally is smaller than the whole state space. This is the closed interval CD, and it is an event that the random variable s, small s, falls into the interval CD. So a probability measure assigns values to any of these intervals, because with the probability measure we can always describe the probability of the event that the random variable falls into any of the intervals. If it is a continuous variable, we can use the density function as the probability measure, because the integral over the interval AB is 1, because the random variable cannot fall outside the state space. And if we choose any interval CD, we can integrate the density function over this interval, and then we will have the probability that the random variable falls into this interval. So this is a probability measure.
Okay, let's do another exercise. This is exercise 7.4. First, point A. We need to show that if we define a function as the sum of two measures, so mu1 and mu2 are measures, we need to show that the sum of the measures is also a measure. The exercise is simple because all we need to do is to show that all the three basic properties of measures hold in the case of lambda a. So for instance, for the empty set, this equality holds, which is 0, so the first basic property holds. It is also true that for any set A, lambda is non-negative because the two functions we are adding up are measures and they are non-negative. So these are the first two basic properties. There is a third one, the crucial adding up property. It takes some thinking, so let's do this together. So we need to show that the measure of union of disjunct sets is the sum of the measures of the disjunct sets. So it's equal to this, we just use the definition of the function lambda, and at this point we just simply use the fact that both functions mu1 and mu2 are measures and the sets are disjunct. So this is what we have. So we traced back the function to the sum of sums, and altogether I insert one more row to be clear. So lambda is a measure. Problem B is related. We define a function on the basis of a measure mu1 is a measure, and we want to show that the function lambda is a measure. So the task is very similar. So let's focus on the three basic properties of measures. The intersection of the empty set with any set is the empty set. So this is 0. This is 0. So the first property holds. It is also clear that given the fact that mu1 is a measure for any set A, the function lambda is non-negative. So all we need to do in detail is to check if the adding up property holds. So let's do this. Let's have a series of disjunct sets just like previously, and let's put this series of sets into the measure. Yeah, this is what we do. Here we have an intersection, and let's use the fact that this intersection can be described as a union of intersections. So instead of the intersection of a set and the union of sets, we can write the union of intersections, and here we use the fact that these sets are disjunct sets. So we use the fact that these sets are disjunct, and we also use the fact that mu1 is a measure. So in its case, the adding up property holds with no problem. So yes, the adding up property holds for lambda 2. So lambda is a measure. In exercise 7.5, we assume that we have two sets in the sigma-algebra, and one is the subset of the other, so we have something like this. And to solve this problem, we can introduce a new set as the difference between B and A, thanks to which we have some very favorable consequences. First, note that the union of A and C gives B. This is one favorable, very good consequence. And the other is that set A and set C are disjunct. So, thanks to the fact that mu is a measure, we can write the following. So, the measure of set B is the sum of the measures of the two sets because they are disjunct. And given the fact that, so this is a main result which is very useful, and given the fact that mu is a measure, so it is non-negative, it follows that the measure of set B is higher or equal to than the measure of set A, and this is one of the results we were supposed to show. From this equality, it also follows that the measure of set C can be described as the difference between the measures of set B and set A, which is equal to B minus A, because C is, by definition, is this difference. So if the measure of set A is finite, we have this result, which was the other result we were supposed to show. We are done.
We saw above that if we have a Borel set, a closed interval, and if we have a density function, we can use the density function as a probability measure. And we also saw that this probability measure can be used to describe the probability of the event that the random variable falls into a Borel subset of the interval we are working with. And if we make the calculations, we always see that we have a probability, so we can calculate a probability for any Borel subset we are working with. But so far we have had no formal proof that the integral is applicable to all the Borel subsets of the closed interval AB. So what to do now? We have a strategy of 3 steps. First, we will use a smaller family of subsets instead of a sigma-algebra, which can be too big a family to work with. So instead of the sigma-algebra, we will use a smaller family of subsets called algebra. So first we will define the algebra. we will define a measure on the algebra, and we will, as the last step, as the final step, we will extend this measure from the algebra to the sigma algebra. So, plainly put, the sigma algebra may be too big to be to define a measure. So instead of the sigma algebra, we will use a smaller family of subsets. We will define a measure on the algebra, and we will extend this measure to the sigma algebra. So first of all, let's define algebra. It's very similar to the sigma algebra. So you can see that the empty set and the whole state space is in the algebra. It is closed under complementation, but the third feature is the most important. The algebra is closed under finite union. So it's not closed under infinite union, it's closed under finite union. So in this sense, the algebra is a narrower family than the sigma algebra. So now we have a smaller family of subsets, and at this point we can define measures on algebras. So let's define measures for algebras. Just like in the case of algebra and sigma algebra, the measure for algebras are very similar to measures for sigma algebras. So for the empty set, a measure on an algebra gives 0, it's non-negative, but the third feature is the most important one. If there is a sequence of disjoint subsets in the algebra so that their infinite union is in the algebra, then we have the usual adding up property for infinite union. So if we make the infinite union of the disjoint subsets, then the measure of the union of the infinite union is equal to the sum of the measures of the disjoint subsets. What's the point? You may ask. If you go back to the definition of measures defined for sigma algebras, you can see that in that list there was no point about so we didn't have the last feature, namely it wasn't required that the union should be in the algebra. So a measure defined on an algebra can be used for infinite unions only if the union is in the algebra, because a sigma algebra is closed under infinite union. So we didn't need to pay attention to the question of infinite unions. If there is a sequence of subsets in an algebra, their infinite union must be in the sigma algebra, because the sigma algebra is closed under infinite unions. So this is the reason why it was natural that the adding up property worked for measures defined on sigma algebras. But algebra is not closed. It's not required to be closed under infinite unions. So a measure defined for an algebra can be used for infinite unions, but only if the infinite union is in the algebra. And just like in the case of sigma algebras, for finite unions we don't need to pay attention to, because algebras are closed under finite unions. So an algebra is a smaller family of subsets, and than the sigma algebra. And on algebras, we can define the measures which can be used for infinite unions, but still it's easier for us to define measures on algebras than define measures on sigma algebras. Having all this in the bag, the next step to take is to extend the measure defined on the algebra to the sigma algebra. Formally put, what we are looking for is a proof that ensures that if we have an algebra and a measure defined on this algebra, there is a sigma algebra and the measure on this sigma algebra, so that the measure, the two measures are equal for any given set. So if there is a set in the algebra and in the sigma algebra, the two are the same, because if the sigma algebra contains the algebra, any set in the algebra is contained in the sigma algebra too. So if there is a set in the algebra, then the two measures are supposed to be equal. So first of all, to do this, we need to define a measure, an appropriate measure on the algebra. We have a to the sigma algebra. We have a measure defined on the algebra, and on this basis we want to define a measure to the sigma algebra. To do so, we seek a series of sequences of sets in the algebra, and we define the measure for the sigma algebra as the infimum of the sum of the measures of these series of subsets. The measure for the sigma algebra is going to be the infimum of these possibilities. So practically speaking, we look for subsets, series of subsets in the algebra, so that a given set is in the union of these of this series of subsets, and the measure for the sigma algebra is the infimum of this set of measures. This measure defined for the sigma algebra is called the outer measure generated by mu, the measure defined on the algebra. This outer measure, this is the candidate, this is our candidate measure to be the measure for the sigma algebra, has some distinct characteristics, some key characteristics, of which the last one is the most important one, because the first 1, 2, 3, 4, the first four is very common. So the first four features are what we expect from a proper measure, but the fifth feature is problematic, because you can see that the countable additivity doesn't hold for this outer measure. So it may hold, but it doesn't necessarily hold. So you may remember that additivity, the adding up property, is something we insist on badly. So this is not something we want to say goodbye to. So we want to do something, we need to do something in order that we could have the crucial adding up property. So the strategy is to focus on a smaller sigma algebra that still contains A, the algebra, but this sigma algebra is such that the measure has the adding up property. So first, once again, we restrict the measure for to a smaller sigma algebra that still contains the algebra we are interested in, but over which the candidate measure for the sigma algebra is countably additive, so it has the adding up property. What family of subsets, what sigma algebra is the most appropriate? If we are smart, and let's be smart, we can find a sigma algebra that ensures that the adding up property works. Let's focus on the subsets on which the additivity works for sure. So a subset A of X is mu asterisk measurable. Okay, let's skip the formal definition. So let's collect the subsets of A for which additivity holds. The collection of all the measurable sets is denoted by A asterisk. So this is a sigma algebra. So it can be formally proven that this family of subsets for which the adding up property holds forms a sigma algebra, and on this basis we can formulate a key result.